now live streaming. So now what I'd like to do is introduce Jenny Chow. She's a former student of mine. You get 2 tries at the quiz. Yes. So on Wednesday, you'll get 2 attempts. Again, if for the, yeah, you won't have time to do it twice. I doubt it, but yeah. So Jenny is a former student of mine. She's electrical engineering. She's up at Cal Poly. She's finishing up and she's interviewing for jobs all over, and she's done a lot of internships. Some of you may have met her in another class, and if so, that's cool. If you haven't met her before, I thought we'd have a brief talk and let her go over. And since we're doing Gauss's law tonight, Jenny, we should try and shoot to keep it maybe around 20 minutes max. So just kind of keep an eye on the clock, because I do have to crush their souls with Gauss's law a little bit later. All right, so I'm going to let Jenny do a brief introduction of herself, maybe talk a little bit about Hancock and what the transition was like. And then at any time, you can ask questions in the chat, and then she'll keep an eye on that and start addressing it. So without further ado, let's get to Jenny.
Hi, everybody. I'm Jenny Chow. Gauss's law, I actually had to use that recently, last quarter. We're talking about electromagnetic waves in one of my upper division classes. So as Jorstad mentioned, I'm in electrical engineering at Cal Poly, graduating at the end of this year, finally. I first came to Allen Hancock in 2011, so almost 10 years ago at this point, transferred in 2017. And my story there is that I didn't know what I wanted to do when I first went to college. So I started out as interior design and then hated that and jumped into engineering and just kind of narrowed that down into electrical engineering along the way. I went through a couple other majors within engineering before I figured this out. But I'm here now, and during my time, I've done, oh, this is a really big class. Wow. So during my time, I did 5 internships, 2 of which were before I transferred. And I've also had some really, really amazing scholarship opportunities. So I've never had to work during the time that I'm at Cal Poly. I worked a little bit when I was at Allen Hancock College. But I'm debt-free from that, and I get to live a pretty nice lifestyle from that as well. But I've still been able to additionally get like some extra income from my internships as well. So a little bit about the transition to Cal Poly from transferring. I've always felt so grateful that I came to Allen Hancock College for my community college experience. Like all my professors at Hancock, Jorstad, Don Del Bello, and a couple others that have retired since have like really prepared me well for the experience, both for after transfer, but also for working in the industry. So like I've had industry experience from my internships, and I'm going into full-time jobs soon here. I feel so confident because of my foundation, my base that I was able to develop from the way just that my professors at Allen Hancock like pushed me, right? Like it's really hard work and the standards are really high, but they're high for a reason. They're like not just trying to make your lives miserable or my life miserable at the time. You know, like it really sets you up for success. The teachers at Allen Hancock, or at least the ones that I've had, have been like very intentional about why things are difficult. You know, so that by the time you transfer on to wherever you're going, whether it's Cal Poly or otherwise, like you'll be ready to take on more, because it's only going to get harder from here. You know, contents are only going to be more technical no matter which engineering branch you go into. And if you can really get a very good solid grasp of these like foundational things, even if they seem a little bit boring and pointless, like it'll get you so far. It'll make you that much more successful. Oh, you're muted.
Sorry about that. Yeah, so I just said right on. I was going to say, and remember, anybody, if you want to ask questions at any time, go for it. Sorry, I didn't mean to interrupt.
Oh, no, you're good.
Yeah.
Yeah, ask me anything about like scholarships, internships. I'm also doing a lot of full-time jobs now. Yeah,
I'll start it. Oh, could I start it off with a question?
Yeah, of course.
So I'm curious. So you're now finishing up your EE, right?
Yeah.
And there's a lot of people in this class that might want to be EEs, or maybe they haven't thought about it. Is there anything you could tell them about why you think EE has been good, or what about their prep they should do for EE? Is there something you could recommend? How much coding are they doing? Oral presentations, all that stuff. what is your experience in real life with your internships and also just at Cal Poly?
Yep, that's a really great question. So electrical engineering. So I actually started out as environmental engineering when I first dove into engineering. Went through a lot of stuff, so I'll try to keep this short. Basically came to the conclusion in my last year at Allen Hancock, realized that maybe this isn't quite right for me because I wasn't really enjoying the classes that I was in working towards EE, such as statics. But at the same time, I was taking Dorset's 163 class, the class that you guys are in. And even though I wasn't very good at it
Hmm.
compared to other classes, I really enjoyed the type of challenge it provided. Um, it was the right technical level for me, and it felt very much like puzzle solving and like very investigative type of work, which is where I like to be. I now know for sure. And then so just kind of from that, I took circuits the next semester just to see if I wanted to do it or not, and I absolutely loved it. And then basically just kept going from there and kept narrowing down what I want within EE as well. What was the other part of your question?
Oh, I was
Oh,
wondering, how I do stuff like oral presentations, coding, things like that. I'm just curious what it's been like for you in college, but also in the internships.
right. So I'm really glad that you asked about that because although presentations seem very, very daunting, that's just the reality of how it is,
Mm.
both in college and outside of college. So every one of my internships, I've had to do a technical presentation about
Hmm.
what I just did. And then even just recently in a full-time interview, I also had to do a technical presentation over Zoom. So presentations are super, super important. And at the time that I took 163, I think that was the first time that
First
you
time
were
I did a
doing presentation.
163. Yeah.
Yeah, it's super, super important. Because like your first experience of it is like definitely super nerve-wracking. There's like, oh my gosh, how do I talk about all these technical things in an understandable way when I barely understand them, maybe, but it's a really try not to be too afraid of it. Like treat it as a really good first time look, um, and a first time experience for you to get all the nerves out so that like later on when you have to do them in your other classes, when you have to do it for a job prep or whatever, like you're already on top of it. So like that kind of thing definitely prepped me a lot for Cal Poly and for internships as well. What was the other part of your question again?
Oh, coding.
Coding, yes. So for EE, there's a lot of routes you can go in EE. Some of it does not require as much coding, but everybody should know some coding for sure.
Mhm. What
So
about mechanicals and other? Is everybody pretty much doing some MATLAB or Python at some point up there in all branches?
as far as I know, yeah, it seems like all of engineering does at least a little bit of programming. I mean, some like within EE, we kind of laugh about MATLAB being programming, but
Oh,
but it,
right,
it
right.
still is. I
Yes, yes,
I
yeah.
think it still is. But so like there is definitely still some level of programming amongst all engineering, just because it's required to do like simulations, which is also extremely important in industry, actually. So I've heard that you guys are doing some simulations now, and don't
Hmm.
think that you're missing out too much by doing that because a lot of times you want to simulate your designs before you bring it to life because it's much more costly to like make something wrong and have to experiment with it than to just do a simulation from the get-go. So
Yeah.
coding is super valuable for that, but especially in EE, we do a lot. We try to automate as much testing as possible. So there's a lot of
Mm,
involved in
mm,
that. If you want to get into robotics, it's definitely super important because robotics involves it's a very much a cross between like hardware and software. So it's super useful to have both of those under your belt.
uh, sorry to interrupt. I'm curious. Oh, so Aldair had a question too, but before we get to that, sorry, Aldair, I'm gonna sneak in here and scoop you here. I'm curious if you talk with a lot of CS majors because it seems like I get about a third of my class is now CS majors. Do you have a lot of friends that are CS majors, and do you have any comments you might, uh, I guess, any reflections on what their careers are like if you happen to know anything about it up
Yeah,
there?
so I
Sorry,
think a
my
lot
kid
of
came in.
times, no, you're good. A lot of times we kind of, when we think about programming, it kind of encompasses all of programming, but there's a pretty clear divide between the way computer science people program and the way EEs or
Mm,
CPEs, computer engineering
hmm.
program. So um, Opportunity-wise, CS is definitely extremely impacted. Is that the right word?
Oh,
Impacted?
yeah, impacted. So a lot of people, not a lot of jobs.
A lot of people, an extremely like large pool of people to select from, but not enough jobs to fill.
Hmm.
So it's so competitive in CS, and you'll see that even in college applications, it's the most commonly the most impacted major.
Wow.
In
Okay, I didn't know that.
yeah, so at Cal Poly, it's almost impossible to transfer into CS. Just in general, not in general, but if you're in another college and trying to transfer into CS and you're already at Cal Poly, even that's like nearly impossible. It's
Yeah.
really difficult. So CPE and EE offer a lot more opportunities. And again, as far as programming goes, I see them as a very clear divide. CS tends to do more what you think of as traditional programming, where you're just doing a lot of stuff on the computer for the computer. For EE and CPE, you're doing a lot more hardware type of programming. So that means like programming a microcontroller like an Arduino or things of that nature, hardware programming or FPGAs. I don't know if you guys know what that is, but yeah, so it's quite different. Definitely, if you're considering one of those three or even software engineering, definitely you want to think carefully about is that chance of competition and less opportunity worth it or not to you?
Hmm.
I feel like if you want to get into CS as a career, it's probably much easier to go into either EE or CPE first and then double back to that, just because it's just so competitive right now. It's really difficult.
Wow. Have you talked to CS majors or something going to job fairs? Do they just like, man, I'm getting killed out there, or like, do you have friends that are just not getting any callbacks or not getting any
Yeah,
offers?
definitely. It's just so competitive. I see someone in the chat mentioned the GPA requirement. Yeah, it's high because it's competitive. They need a way to weed each other
Yeah.
out. So, I mean, if you feel like you're an extremely driven person anyway, and you're really good at having extra things on your resume more than like anybody else, even you're still in competition with other people that are that way too. It's just a really difficult field to get into right now. Like I said,
I gotcha.
I think if you are EE and CPE instead and then go into a CS job, it's a little bit easier because you have extra hardware experience that may or may like it's just like extra stuff
Yeah,
that
yeah.
you fit in better. So yeah, I'm not trying to like bag on CS being a bad major. It's
No,
just
it's good just to know
that's
what
the
you're getting
reality of
yourself
it.
into.
I
So
actually have a little information about that if you'd like to know.
okay. Yeah,
Um,
let me
my
okay, go for it. And then we'll
my
get to Aldair's
mentor,
question, all right?
my mentor is a engineering mentor at Cal Poly for the Engage Scholarship, and I was asking about the same thing because he was also telling me that it's very difficult to get in Cal Poly through CS, and he suggested other people to go through mathematics
Mm.
because mathematics and transferring from mathematics to CS is a lot easier than transferring from engineering
Hmm.
to CS. At least that's what he told me. So.
Okay, that's good beta. Um so that's good stuff. And it looks like this is pretty useful. I definitely want to get to the Gauss's law stuff, and so I want to get to working through the questions here. So can we get to Aldair's? Do you see Aldair's question? He says, "What are good places for internships for EE?" Do you have any reflections on that, Jenny?
Yeah,
And then Ryan, I saw you had your hand up somewhere, so I'm going to do Aldair, then Phil, then I'll get to Ryan, and then we'll go to Hector. Okay.
sure. Yeah, I'll try to get through these pretty quick. And if you guys want me to elaborate, I'll leave my contact information so we can have like a more
Yeah,
detailed
for
discussion.
sure.
But so internships for EE and even just in general internships, after transfer, it's not going to be hard to find them. They're going to be everywhere, especially at Cal Poly. They're just jobs are always being posted by your department, flyers everywhere, emails, career fair. LinkedIn right now is the best place to look for them. I've actually gotten a couple or several opportunities off of LinkedIn. So if you guys don't already have that, you should make one. In this virtual time before transferring, it's a little bit more difficult. You don't have as many choices, but like I was telling the other class, some of the really large companies such as Google have specific programs for first year or transfer students that haven't transferred yet. So don't think that just because you're a transfer student that hasn't transferred yet, you don't have as many opportunities. They're out there. You might have to look for them a little bit more, but they're there. Like I said, I've done a couple before I transferred as well, and those were both through UCSB's programs. So that's one of the easiest ways to look for internships that require less experience is look for, they're called RAUs, research experience for undergrads, because they don't require as much technical knowledge. It's more like you get into the lab and they teach you everything you need to know to get started. And for engineering, research might not be the most appealing, because I felt that way when I did mine, but engineering research is different. It's not the same as like the type of research you might do in biology or chemistry. Engineering research is a lot more involved. It's a lot more engineering like you would want it to be, and it has more to do with like instrumentation. So like in one of my REUs, I actually got to work on a Doppler LiDAR system for a federal agency, and that was a really cool experience because it was a very specific type of setup that had never been done before. And I got to research something and like help towards like this really big cause for like, what was it for? It had to do with like checking atmospheric conditions and improving ways to look for that for climate change and such. So engineering research is really cool. Don't discount that. Hope that answered your question.
Yeah, and then I see Phil's here. Phil says, I know Cal Poly has software engineering. Is that just as competitive? Maybe you addressed that a little bit. Maybe you could touch on that again.
Yeah, so I'm not as knowledgeable about software engineering. I know it's different than CS though. So in my mind, the way CS and SE work out, SE software engineering, is that CS is a little bit more technical. And SE also involves programming, but it's more focused on user experience and like higher level programming, if that makes sense. So user experience as in like how do you scroll through this app on the phone, you know, and how to program around that. So that's a little bit of the difference. I'm not sure about the competitiveness. I don't know too much about that. I want to say that SE is a little bit less competitive, again, because you have different set of skills. So it's not just the programming, but they take a lot of like, what are they called, kind of design and psychology classes, because it's all about user experience, right? You have to learn like how to interact with people through technology. So it might be less competitive. I think definitely if you're interested in like very heavy programming, I would go into SE over CS just for the competitive advantage. But I think also in our modern age, we don't have enough engineers that can bridge that gap between human experience and technology. Like a lot of times in technology, we're trained to think logically, but people don't act logically. And so a lot of problems in the world are actually because there's that disconnect. So that's where like software engineers come in really handy. And actually like some schools are starting to be more aware of like how to teach design for people as well. And actually there's a really great book I'm reading right now about that by Don Norman, who used to work for Apple. But anyway, I don't want to go off on a tangent too much.
No, that's good. Ryan, you had your hand up. I don't see it right now on my screen, but are you still there, Ryan?
Yeah.
You want to just say something? Yeah, go for it.
Yeah, sure. So less major related, but what are one or two things that gave you trouble or you found hard with transferring, just the transfer from Hancock to Poly? And then what are one or two things that you did to help with that or cope with it or make it better?
Yep, that's a great question. This might be specific to quarter system, but Cal Poly is on the quarter system. So going from you guys are on 16 weeks of the semester to 10 weeks in a quarter was pretty rough. Like all of a sudden, you can't afford to slip up. Or if you do, it's really, really hard to catch up. So that's where it's super, super important to learn like your time management skills and priority skills. So if you're a perfectionist, like I used to be, I wanted to get like all the straight A's. I wanted to get 100% on everything, every project, every lab, all the things. And I was able to do it for a little bit, but at the cost of my health and a lot of time and like even like relationships. I'm not even just talking about romantic relationships, but just like familial and like friendships. Like I sacrificed a lot for it, for perfectionism, and it was definitely not worth it. I felt like I wasn't doing it for the learning anymore. I was just doing it to do it. So, you know, that was one of my biggest challenges going in, both personally and as a student, is like letting go of that. And like, because it just isn't practical. You don't have time in those 10 weeks to be doing things like that. So super important to prioritize yourself. And you might not be going into a quarter system school, but even on a semester system university, you still, like, the work's only going to get harder. You're only going to have more work. So you still have to learn to prioritize. You still have to learn like your time management. It's much better to pace yourself over the weeks than to just cram at the end. I'm sure you all know that anyway, but especially true after transfer. Kind of the second thing that I was challenged with is being, especially at Cal Poly, being a minority. That was kind of difficult. That was something I was not expecting to have a hard time with. So I don't just mean a minority as like a female Asian engineer, but also as a transfer student. So I'm a minority in every way, in that way. Being a transfer student, being older, you know, being a female engineer in EE, which is like, there's only like 3 of us in any given class, which is pretty crazy. You know, all of that. So that's been really challenging. And the way to combat that is it's very much a mental thing. For one, you have to realize that even though you're different, you can look at that as a good thing, because you're different, you bring a new perspective and a different perspective to not just your career, but people around you.
Yep.
Right? Like, innovation doesn't happen because people think the same. Innovation happens because there's those that think outside the box, and that could be you, because you have a different perspective, a different experience. So that's one thing. But the other thing too is to like find people that are similar to you, whether that means like similar in like their other transfer students. Maybe I find other Asians. I actually ended up hanging out with, most of my friends are Hispanic, so I joined a club called Society of Hispanic Professional Engineers, and that was my place that I felt belonging. You know, like, really don't be afraid to reach out and find your people, whatever that means to you. Find your people, find your community. Maybe it's in volunteer work, maybe like the hammock club, I don't know. But there's literally so many communities, small group communities at Cal Poly. Like, you can find your sense of belonging, and once you have that, it might not seem that important, but it is important, because if you're not comfortable where you're working and you have to deal with that daily stress and anxiety of like feeling super out of place, it's definitely going to affect your work and your motivation. So yeah, wherever you transfer to, make sure you find that support and help each other get through.
I'm sure all of you are going to feel a little bit intimidated to be like, oh, I'm just a lowly Hancock student. But I think what you'll find is your academic preparation is all there. You don't know the stuff like where the library is or those kinds of things. But since you're only going to be going to school via Zoom anyways, that doesn't matter anymore. Ooh. Oh, sorry. Okay, so I've been waiting for this one. I see Hector's question. All right, you see Hector? He says, be honest. Have you ever used crap like this? All right, tell the truth, Jenny. Now she's an EE, so it's going to be a little bit different.
This? And have you ever used it in your internship? I feel like Jorstad's making us suffer for the heck of it. Okay, really great question.
You won't hurt my feelings at all, Jenny.
All right. Yes, I used it a lot at Cal Poly, for sure. You know, it might seem really tedious to like rearrange the equations or check units and whatever, but those are there for a reason. It's for you to check your math. And like, if you're not able to check it in the intermediate steps and you get to the end and it's a totally wrong answer, you're going to have a really hard time going back and figuring out what went wrong. A lot of the soft skills, I think, more importantly, is what I've been using. So the presentations, I mentioned that already, but wow, those are so important. How to present your work is like, that's everything for a company. So not just in school, but when you go into industry, like, that could be the difference between you having your job or not. Yeah. If you're able to communicate your work, it could be the difference between you having a promotion or not. It's so important. Like, it's great if you can do the work, But if you can't tell people what you did, it really doesn't matter, right? You may as well have not done anything if you can't tell people what this means. So definitely that's a huge thing. What else? Like the way, okay, this is a really huge thing too. The way Jorstad made us do lab reports, kind of tedious in a way, but wow, like I've gotten a lot of good feedback from each of my internships on the way I document things. And I've actually helped my company, one of my companies, like find this like really weird issue that happened to them that they couldn't quite figure out. I don't know if I can talk about it too much, but yeah, because I documented it and was really good about documenting it, I could then like pass this information on to my team, and they were then able to figure out what went wrong there. So
That's
documentation
cool.
was that.
Oh, I just said that's cool.
Yeah, it felt really good. So documentation is kind of a lesser known skill that's like not necessarily in the job description, but is that one thing that will definitely make you stand out a lot. So I think those are definitely one of the most valuable things I got from Jorstad's classes. Just the whole problem solving process. And I don't know if I can say specifically what, but like prior to Jorstad's class, I felt like I just memorized stuff a lot. I have really good short-term memory, so I can get away with that. But coming into Jorstad's class, he wouldn't let us get away with it, like it was more about approaching the problem critically and being creative and about how you solve it and actually having an understanding of the stuff to solve it, and that got me. I've even recently used those skills at a full-time job interview with a really large company. Like in my technical interview, they gave me this like random problem that I'd never encountered before and asked me how would I solve this. And it might not have been exactly mathematically, but I still like this class teaches you to do it in any context, right? Not just when you're doing the math, but even if you're just presented something verbally, how would you go about solving this? So,
Gotcha.
so
What about
I
Python
don't feel
on
like
the
it's hard
job?
for no reason. Sorry, what was that?
What about Python on the job? Is that anything you've used or not? Or is it growing, or you're closer to the real world than I am? So what's your what do you feel about that?
It depends on what field you're trying to get into. I think Python has now become kind of the minimum programming level that you should have behind your belt. Like if you have no other programming skills, you should at least have Python because it's relatively easy to learn compared to all the other languages. And it can be applied to almost anything. So you can program hardware with Python. Generally they wouldn't, but at least you have the knowledge for it. You can automate a lot of things with Python scripts. You can go pretty low level with Python, even though it's a high level language. You can do a lot with it. So I think Python definitely is like a skill that almost everybody in electrical engineering, even other engineering, has at least have encountered a little bit of.
I gotcha.
So I actually didn't learn Python until recently, last quarter, but I did have C programming and MATLAB under my belt. So I had those going for me.
I gotcha.
But yeah, once I learned Python and had that on my resume, it became that much better.
I gotcha. Sorry, I keep jumping around, and we're probably going to have to get to class here. I know this is good. By the way, if you're worried about me getting the content done, if we don't get it all done by Wednesday night, I can make an extra video or something. So I do think it's important that we take advantage of Jenny while she's here. Let's get to Alexis, and then probably after that, we should probably kick you out of here and get to work. Or you can stick around if you want to make fun of me. But yeah, I see Alexis asked, were you using a lot more math, like complex analysis, Fourier analysis, PDEs? I'll let you have, okay. I have a guess what you're going to say, but yeah, go for it.
Okay, I guess that's kind of similar to the previous question about if I ever use stuff. And I think I didn't answer that part of the question. So in industry, no, you probably won't be doing this math again because most of it's automated. Depends on your field again, but it's not the math. I mean, right now the math is important, obviously, but it's more about the thinking process, the critical thinking, the logical thinking. Like that's why you're being put through all this like suffering, as you like to call it. That's why you're being put through this. And like I said, again, in my interviews, like even though I'm not specifically told to do the math, It's all about how you're trained to think about stuff, and that's what all this math, that's what all these like low level concepts are for, is to teach you to think critically and also teaching you to learn how to learn. So math, like I haven't used them on the job at all, or I have a little bit, but not too much. I've definitely used them in my upper division classes. So my electromagnetics class was very math heavy, and also I had a signals and systems class that was very math heavy too, and that was largely using like Calc 4, Calc 1 type of stuff. Gauss's law, as you guys learn here soon. So yeah, I don't know if that answered your question, but yeah. No,
Sorry to bring it down, Hector. Sorry about that, bud.
You're just gonna have to get through it. But you know what? School, I've heard this from a lot of people, school is the hardest time you'll have in your career, unless you decide to go into research also. That's like a whole nother story. But you know, in industry, once I've gone into the internships, I've found it to be way easier than what we're presented in class. But again, the point of class is to teach you how to think critically, how to think logically, how to problem solve, how to learn, so that once you get in there, you have all of those things and they're going to be second nature to you. That's the point of all this.
Yep. All right. So I could keep talking about this all night, but we should probably, everybody, if you can figure out how to do those reactions, let's give Jenny some love here. Give her a thumbs up or something. All right. Or yeah.
Guys.
And really appreciate her coming in. And I think, Jenny, if you, do you usually tell people they can find you on LinkedIn or whatever, or Facebook or something?
I'll put my social media stuff in the chat here, and whatever unanswered questions there were, I'll write an email to you and you can forward to them.
Yeah, that sounds perfect.
But yeah, don't hesitate to reach out, you guys. I'm always happy to help. I know, like, you know, it wasn't that long ago that I was in your shoes. You know, I transferred in 2017. It's not too long ago, and I'm always happy to help and give insight, whatever you guys need or want, especially while I still have time right now and quarter hasn't started yet. So yeah, don't hesitate to reach out about anything.
Right on. All right. Someday she may be your boss. So, all right. Thanks again, Jenny. I'm going to go ahead and get to work here. So, all right. So now I'm going to talk a little bit about Gauss's law. Let me see here. All right. And that was really awesome that Jenny did that. I just love that she's willing to come back and volunteer her time to talk to you. And I hope that you guys found that useful. And feel free to ask me any questions over email and I'll get that. And yeah, so if you have comments about that or things that you learned or had more follow-up questions, send them in my email and we'll get that later. So now let's go ahead and get to it. Jenny, I don't know if you're still out there. You might find this kind of funny. But yeah, I actually got the hard copy of the E&M book now. Finally, this is the first semester I'm using it. It's a big deal for me. 10 years in the making. Anyways, so now I know a lot of you don't have this yet. And remember, the first 3 chapters you can get on there. So I'm going to go ahead and screen share. Let me get that going here. Oh, whoops. We'll do that later. Let's go to this one here. Whoops. Oh, Zoom. All right. So hopefully all that torture and stuff, it's, you know, it's the kind of thing where if you don't get tortured with it here, you're going to suffer there later. And I would rather you guys suffer with me for low cost per credit unit and have you hate me and then go on and have lots of success there. So, I mean, yeah, that's just my philosophy. I'd rather have you guys get as much of these stupid little details learned here so that you go on and just rock it. So that, I guess that's my philosophy, and that means we do a lot of work here. And it is, Hector, it's no joke. You're absolutely right. This class is a lot of work compared to the average class, but hopefully, you know, it's basically, you got to do the work at some point in your career and you're getting stuck with it now so that when you have all those complex issues that happen after you transfer, I'd like to think at least your foundation is solid and you can focus on the academics a little bit easier. All right. So we're going to talk about electric flux and Gauss's law today. So electric flux is this is capital letter phi, by the way, this letter phi here. Oops, let me get this right there. That's a capital letter phi, subscript E for electric. So if you see here, we're going to do the integral of the electric field dotted with the area vector. I'm going to go through that in just a minute and show you here. So dA is a differential area vector. And this is kind of all you need to know about that. It has units of meters squared, and it points perpendicular to a surface. So you can see here, if I just scroll down and show you these two examples, it can be a little bit tricky. Let me get my controls back. So you could have an area vector that points perpendicular to this surface like this. So this could be dA. And then flat surfaces are actually a little bit trickier than curved. Usually we say it points radially outward. So this would be an area vector. Now, if you're wondering what the dA means, what does this little d here stand for? It means a small chunk of area. So you take a small chunk of this sphere, and that would be dA. The whole sphere has surface area A, but this tiny chunk can be thought of as a little bit of vector. Like think about my forehead here, right? It's pointing outwards. Oh, let's get this marker, right? So if I put this marker there or in different spots on my head, it's pointing outwards. Now, in general, what you do is you think of the surface as like a flat surface. This is where it gets tricky. If my hand is considered the surface, you could be pointing this way or that way. Generally speaking, we usually just pick whatever's easiest in the problem that gives us the fewest minus signs. For example, in this problem right here that I'm drawing, you could call this dA, or you could call the other side dA, but since all the arrows are going to the right, we don't use this one. We use the red one there. And again, apologies if you're colorblind there. We'll use this one here. All right. So again, we have a right, and this again corresponds to a small chunk of that surface, not the whole thing. Okay, so that's what the area vector means. Whoops. All right, and we'll do a problem in just a second on that. There we go. Get up there. Come on now. All right, and so now what can electric flux, if you're trying to think about electric flux, and I see there's a lot of questions in the chat. I'm going to get to them in just a sec. Appreciate your patience. Electric flux, you could think of this as the number of electric field lines penetrating through a given surface. And that's why I had this simulation up and running here. The idea here is you could see this is the electric field, right? And so here I chose a negative point charge, right? And you can see that there's all these electric field vectors. If I could get my annotation going here. So here's an electric field vector. Here's another one. Notice this one is going through the surface. This one's going through the surface. And I don't know if you could tell, this one is, and I bet that one is too. This one is. And so the idea is we see that some electric field lines are going through the surface, and this one is not. This electric field line is not. So you could think of the electric flux as the amount of electric field lines going through a surface. Now, in this case, the box that I drew, this gray box that you see here, that is actually a special type of surface. It's called a closed surface because the surface is completely enclosing the charge. And that's where Gauss's law becomes special. So, and obviously there's many different types of surfaces you could use. You could use a cylinder, you could use a sphere, you could use, those are all going to end up being closed surfaces. And those are the ones that we're going to focus on: boxes, cylinders, and spheres. Why? Because boxes relate to plates. Cylinders relate to wires, and spheres relate to point charges and things like that. So what we're going to do is we're going to try and understand how this electric flux, these field lines through a surface, relate to the charge inside the surface. Again, we're going to relate the electric flux, the field lines through the surface, to the charge inside. Now I'm going to get to the chat here, and I'll stop for a second. Where was that chat button there? Okay. Oh, right on. Oh, okay. Yep. Surface integral. So, okay, cool. All right. So let's take a look. And I don't usually like to do this, but so we can get through this first problem, I'm just going to go straight to the solution in this one. All right. So I know you could read it later, but I want to talk about this problem here. Whoops, this problem here. So if you want, and I even say follow along with the solution for this problem. So the idea is, let's try and get a really basic idea and try and do all this stuff. So we're going to try and figure out the electric flux for this surface. What do we have to do? First, get the area vector, compute this, and then we could do a variation on that. So what I'm going to do is go straight to the solution and just show you what this means here. The idea here is, if you already know multivariable calculus, that's cool. You could say this is dx dz in this case. Why? Because I've got an I hat here and a k hat here. I'm in the xz plane. So imagine you have a small amount of x distance and a small amount of z distance. Now it turns out in this class, multidimensional calculus is not required. That means you're going to see me teaching it with 1D calculus. Now, those of you that do 3D calculus, you're like, oh God, I hate 1D calculus, right? But remember, the prereq for this course is 1D calculus, and that's how I teach it. So if you want to do it a different way and you want to read other resources, that's cool, but I got to teach it this way because that's the prereq, all right? And this way is just fine. I think it works great. I've actually gotten used to it over the years. So I just want to show you, here's a different way to write this. Here's a small slice of the total area. And again, I'm looking at this strip right here. I have a small strip. It's got height h, width dx. And so that's where I get the h and the dx from. All right, maybe I should get out my annotation here. All right, so I'm looking at how this right here relates to that strip. And notice I just chose this area to point this way. If you're wondering, why did I choose that way? Again, it's because I already have an arrow that's pointing that way. So with the flat surface, you get to choose. Flat, I choose. So you can do that too. Anytime it's flat, you could have chosen negative j hat if you want. All right, so I'm going to clear that out. So now let's scroll down and see what this looks like in practice. Here's our picture. There's the math. Let me get this zoom. There we go. All right, I'll get this thing out of the way. All right, and so here's the definition of the integral. What did I do? I said dA is equal to this thing right here. So again, it was 12 meters because that's what h happened to be in this problem. Dx and j hat came from my choice because it's a flat surface. And there's the coordinate system. You can see it's j hat right there. This was the electric field given in the problem. And then from there, it's just boring calculus. Do notice this fact right here. There's a dot product. You're going to see this a lot. So notice there's the j hat dot j hat. And hopefully you remember that Chewbacca hat dot Chewbacca hat is 1. Taco hat dot taco hat is 1. Any hat vector dotted with itself is 1. That's the definition, or part of the definition, of a unit vector. Okay. And so then here we go. And notice these are the weirdo units you get. That's not that exciting, but there we go. And so let me go back here to the question really quick. So that was this part, determining. And so that was, I figured out the area vector. I had to slice the thing up and figure out some kind of tiny little dx or dy or something like that. And then we did this one. So now imagine if it's through the XY plane. And I want you to think to yourself, if you put it in the XY plane, that would be like putting the surface down here, right? Any electric field line coming in, there's another one going out. And the dot product matters on the direction, right? So you can get a negative term if it's dotted the opposite way. Furthermore, this area vector, gosh, I keep picking red and green, apologies. The area vector would be pointing up in this case. So maybe you could think to yourself, what is the total flux through this similar sized plane? Give me just a second. So we're going to be looking at the electric flux through a plane in the XY plane. Let's go look at it. Hopefully you agree that it's 0. Right? There's the same amount of electric field coming in as going out. Or think about this. Whoops. Oh, come on. The electric field in this problem is in the j hat. The area vector is in the k hat. J hat dot k hat equals 0. And so when you have two things that are perpendicular, the dot product is going to be 0. Let's check here. Oh, so Luke is asking a very good question. It's totally arbitrary how many field lines you draw. And so to that, in that sense, my description of it isn't the best. So for example, if I could go back to here, Luke, right? Oh, whoops. Let me get rid of that annotation. Come on. So Luke, it's totally arbitrary how many field lines you draw, but the idea is it gives us a feeling. You could think about it as the surface is being a net and the field lines are going through it. Now, if you wanted to, I could do the same thing, right? And go in here and I could pick, it's good for comparing two surfaces for the same size charge. So I could do a spherical surface versus a box and I could see how they differ. And for that, I could use a fixed grid spacing and use a certain increment size or whatever. But yeah, so that's only, yep, okay. It's great for comparing two things, but it's not perfect in an absolute sense. All right, good question, Luke. Excellent. Yeah, because it's totally random how many arrows you draw in real life. Okay, so that's good. And now what I want to do, again, we're trying to get to this down here, but I want to give you one more example of this. So I'm going to look at this problem and then I'm going to let you work it out later. So we have a 20 centimeter, a ball of 20 centimeters surrounding a proton. So it would look a lot like this, except if I use down here, we'll just change this to a sphere. Let's just not change the name. So the idea is, give it a sec, right? The idea is now we're going to use, we're going to use this sphere and look at the arrows that are penetrating the sphere instead, okay? So where was I? Right here, all right? Let's go look at the solution, all right? So here we go. In this case, sorry, I guess I'm probably hurrying a little too fast. My apologies. We're looking, what is the magnitude of the electric field at the surface of the ball and the direction of the electric field at the surface of the ball? Well, now think about that. If you have a point charge right here, you know that right at this point, it's K Q over R squared in the R hat direction. So it's going to be pointing outwards, just like these arrows right here. And the magnitude is going to be this, and the direction is going to be radially outwards. Now, so that's what I wanted you to think for parts A and B. Let's go look at the solution to make sure there's not something I'm rushing past. Whoops. Annotate, clear. Okay, so that's what I was trying to get at. Here's the magnitude, right? And you know it points radially outwards. So I was not trying to do anything fancy there. Now, and again, you can go through this slower and pause the video if you need to later. Let's get the area vector of the ball at each point. Now we need to think. This is going to be a little bit tricky for you. So let's go look at that one and see what it turns out to be. In this case, it's the size of the area times the direction. If you want, you could say it's whatever dA is, the magnitude of these little squares here. So again, we're looking at this little piece. There's going to be some size of it, dA, and some direction, dA hat. Well, we already know the direction is outwards. Look at it. It's pointing outwards up there. So we get this outwards right here. That's where the R hat comes in. And so dA, you might be saying, well, what is that? That's the area of one tiny piece of a sphere. And I think I have that written here somewhere. Okay. Oh, I see how I'm going to do this one. So in this case, if you want this, I could add this in. It should be 2 pi R dr, I believe. And so the idea is when you integrate this, let me see here. I better check this. I'll tell you what, I'll update this tonight so I'm not screwing this up on the fly. I'm trying to do it in my head. So you know when it integrates, I may have I might need an 8 pi or something because there's going to be an R squared over 2. So I'll fix that up tonight and put that in the solutions. Sorry, I'm trying to do that on the fly. But all right, this is not the most important part of this problem anyway. So let's get to the answer here. So, oh, and I was just asking about the direction. I didn't ask about that size of it. So now we're going to get the electric flux. So let's go back and look at this. And again, apologies for just keep switching. I will get to the whiteboard any minute. Here's the electric flux. Here's my calculation. Here's the electric field piece right here. So that's the electric field. That's the area vector. And then for this problem, it's a constant value. Think, in this problem, the radius isn't changing. This radius right here is a fixed number because all the points that we're talking about are on a sphere. If we scroll up here, the radius is constant. This has the same radius as this has the same radius as this over here. All those different red arrows have the same radius from the sphere. from the point charge. And so that's what allows us to do this trick. We could pull out this as a constant, and then you're off to the races and you get this thing done. All right, one last piece. We could compare this interesting result to this weird thing, Q enclosed over epsilon naught. And this is what I care about. So if you think I've been rushing through this really fast, you're right. Is this that important up to now? Not really. This is the part we're going to use. So here's why I care about this. Look at this interesting result. Now, if I look at this number right here, this was the answer from the electric flux. Now I notice that these R squareds cancel out. You see that? And K is also 1 over 4 pi epsilon naught. Epsilon naught, if you remember, is just a different way of writing the constant K. This number is something like 8.85 times 10 to the minus 12, okay? And K is basically the inverse of that with a 4 pi. And let's not worry about the units right now, okay? But so the idea is then you have Q, and then you have a 4 pi. Well, look, the 4 pi's drop out. It turns out in this chapter, we're going to have a lot less writing if we just write it as this. So notice the electric flux is equal to the charge that was inside the closed surface, the closed box, over epsilon naught. And this is where this gets interesting, okay? Normally, we could care less about the electric flux, but we oftentimes care about the charge. I'm going to show you some tricks for figuring this piece out. And what that does is it allows us to relate charge to something that's easy to figure out with some tricks. That is Gauss's law. And I want to point something out that's very unusual here. This is where we can go back to that simulation. In this case, it turns out the electric flux is the same whether or not you use a sphere or whether or not you use the square, whether it's a big sphere, big square. Anytime you have a closed surface, the electric flux through this situation is exactly the same as before when I was using a box. And so this is very weird and useful, it turns out. All right, now I've been yakking a long time. I'm going to pause and see if there's any questions here. Any questions on any of that? I know I'm just going really quickly.
So by Q enclosed, that's the amount of charge enclosed in our shape.
Yes, and I want to be careful here. This is true if you have a closed surface. So
Right, yeah.
It's not true if like you did a hemisphere or like this bowl that had a lovely cookie in it at one point that I ate. So right, this is not a closed surface. But if I put a charge in here, let's do it. Oh, there's not much hair there, but yeah, okay. So we got this charge, right? Now it's in a closed surface. I know that the electric flux is the same no matter what I'm doing with this thing, right? It's always going to be the same. It's the charge enclosed divided by epsilon naught. It's like the easiest calculation ever. And then it's a lot of work to learn tricks to make this useful. So, right, again, I put a charge in there. If you close the surface, and that, Ryan, is that good enough on that?
Yeah, definitely.
Okay, cool. And let's do this. Let me see what the chat was. It'd be the same for a rectangle. It'd be the same as long as it's closed. You could use a weird box. You could use a cylinder. Same. Now, in practice, I got to tell you, look at this. I think you could see this right away. Give me just a second. In this case, this is a lot easier to understand for most of us, even though we have to use r hat, because all the vectors and all the surfaces are pointing the same way. It turns out usually for spherical objects, you would never do this problem without a spherical surface. If you had a cylindrical object, you would only use a cylindrical surface. And if you had a giant flat plate that's been charged, you would only use a rectangular surface or something like that. So if I could say it that way, I will. I guess I did. So here's the summary. Here's the important thing right here, right? For any closed surface, that's the result. And now notice example 23.1 is a not closed surface, right? There's no charge that's inside a box. And then example 23.2 is a closed surface. And then this is what I was just saying here, kind of in relation to some of the questions you're saying. Basically, if you have a spherical object, you're always going to choose a spherical surface, cylindrical, etc., and like that. So a small box with flat sides or the rectangular box will be used for plates or large planes. This, okay, we're done. There, that chapter's done, right? I'll just let you figure out the rest on your own. No, that would be crazy. So it turns out, before we move on to applications of this, let's first make sure we understand charge with both uniform and non-uniform densities, all right? And you can see right here, if you don't like listening to me right now, what you could do is you could start going from page 34 and page 35. So I'm going to talk a little bit about those on the whiteboard, okay? And so that's what I'm going to do, just so we can understand charge, all right? And I'll get the question here. Oh, Jenny, thanks. I'll give you that $50 I owe you later. If anyone, yeah, so super cool. Yeah, for sure. All right. So, and those of you that are not going to be double E, I'm not going to lie to you. You're probably not going to use this that much if you're not double E, but since a large portion of you are, we gotta hit this pretty hard. Right on. Okay. So let me go here. So again, you know what I'm working on, 23.3, and I'm just going to write this on the board so you don't have to keep watching this PowerPoint or whatever you want to call it. So give me a sec here. Thanks, Jenny. I owe you one. All right. Okay, so I'm looking at this problem. I'll leave it up while I get it started, okay? Sorry, I forgot that. So I'm going to start working 23.3 right here, all right? What do I have here? Okay. Oh, I see what I'm doing. So first, I'm just going to talk about charge density, all right? So we already talked about lambda, which was the units of lambda were coulombs per meter. We talked about sigma for plates. The units of sigma are coulombs per meter squared. And now, oh, jeez, sorry. There we go. My bad. Units of lambda are that. Units of sigma are that. So this was a linear, that black is dying there. This is linear charge density. This would be area charge density. And now we're going to go to rho, your volume charge density. Rho, the units of rho are going to be coulombs per meter cubed. And that's going to be a volume charge density. Okay. And there are different times where you want different densities. We've already seen for rods and arcs, we usually use linear charge. For plates, we oftentimes use area. And it turns out for three-dimensional objects, we might need to use a volume charge density. So the idea is, that's what we're going to work with now. And I ran out of some room, so let me do it like this. Think about the units. If the units of rho are coulombs per meter cubed, I think it makes sense that rho would be take a tiny bit of charge over a tiny bit of volume. And so this, in general, is always true. Think about it. This is true even if you have a non-uniform density. This is true because you take any one piece of an object. Let's say I had a weird, I don't know, taco or something here, and we charge this taco up. And maybe there's more charge here than there is over here. Well, we do know at this spot, I could take this amount of charge over this amount of volume and get the density at that location. Over here, I could take this amount of charge and this amount of volume and get a different density for this location. That's all a non-uniform density is. It's like a piece of bread, right? There's holes in a piece of bread. And so different pieces of the bread have different density. All right. So anyways, so that's always true. This is true if it's uniform. So this is a big if. If uniform, meaning the bread is basic, I guess, like this book, right? The density of this book, every page is about the same density, right? Because they all have the same amount of worthless words on them. All right. So in that case, that book is all uniform. And so then you could say the density is also Q total over volume total if it's uniform, all right? So if we have a uniform object, meaning the charge is basically equally spread out everywhere, then we could do this trick. This is always true. This is sometimes true. This is when it's true. Okay, so I'll pause there for a sec. All right, and I totally forgot my page and threw some stuff on the floor. Sorry, just a second, just a second. All right. Oh, and so, all right, now we can finally get into that area vector crap that I was talking about. So let's say we have a sphere like this. So let's say this is a sphere. And let's say the radius is r. So just to show that, I'm going to make this and call it 2r. I don't know if you can see that all the way. Okay, so we've got this sphere, and let's say the total charge is q. Now we got to be careful here. We're going to start with a piece of plastic that has the charge uniformly spread throughout the entire volume. We'll learn more about what happens if you have a piece of metal or when the charge is just on the outside. Let's do that later. Let's start with basically assume somehow the charge is uniformly spread out throughout this whole sphere. If that's the case, I know that the charge density, rho, man, I need some new markers already. These things go out quickly. It's Q over what's the total volume of a sphere? Well, that's just 4/3 pi. I'm going to use capital R here. You're going to see, generally speaking, I'm not perfect, but in this chapter, I'm going to try to use capital letters for the total charge on an object, or capital R for the total size of the object, big R. All right. So I could clean this up a little bit. The 3 flips to the top. It should be 3Q over 4 pi capital R cubed. So that's my density. And notice, if Q is a constant, it's not changing. R is a constant, it's not changing. We're not changing the size of the sphere or the amount of charge on it. This would also be a constant. That's what I mean by uniform density, a density that is constant throughout the entire material. All right. Okay, so far, so good. Now what I want to do is make sure, I know this is going to seem a little circular, but what I want to do is I want to verify I know how to go from a density to charge. I'm going to try and use the mechanics of integration to verify I can get back the right answer that we started with. It seems a little cheesy, but let's just do it. So in this case, this is my claim. Q total should always equal the integral of rho dV. Think about it. Let's do the units on this little piece right here. This sucker right here is coulombs per meter cubed. This thing is a small amount of volume. That's meters cubed. And what does an integral mean? Add it all up. So we're going to add up all the little charges and get the total charge. Piece of cake, right? And in this case, it actually is, if you could figure out what this thing is. Now, you're going to see me use a twiddle here. Nobody else probably does this. And so if you're reading other books, you might be like, what the heck is this twiddle? I'll explain in just a minute. So I'm going to just keep going through this. The idea now is this. All right. Let me get a little bit more room here. So in this case, I want to figure out what rho is. Well, that's right here. I've got that. Hey, look, this is a constant, isn't it? It should pop right out of the integral. I could do that right now. Because this is a uniform sphere, that allows me to do this. Now, I know when I integrate this, I have to get back the right volume, but I'm going to go ahead and show you what that should be. Oops. It's rho times the integral of. Now, think about this. I'm going to try and build up this sphere. Man, usually I have some hemispherical bowls to build this, and I didn't think of that until right now. I'm going to try and build this thing up out of shells. I tell you what, give me 10 seconds. I'm running to the kitchen. Imagine you're building it up out of these shells. That's what we're trying to do here. All right, sorry I forgot to do that before. So the idea is, imagine you're trying to build this entire sphere, right, out of all these little bowls. And so each one of these, now obviously I can only show you a hemisphere right now, but imagine these are all the way around. So you're going to build it up out of these and stack them, right? So the idea is this is going to be a sphere with some 4 pi r squared surface area, right? So the surface area of a sphere, it's not a perfect one, but just, okay, so 4 pi r squared. And this would be a different 4 pi r squared. And this is an even bigger 4 pi r squared. And then what's the thickness of it? The thickness, where, here we go. The thickness right there is a small change in radius from the inside to the outside, dr. Okay, so that's what we're doing. And that's why this becomes, let me write it down here. I'm running out of room. Okay. And this is just my habit, okay, this r twiddle. The idea here is r twiddle could be the radius of any of these bowls. Whoops. Again, oh, geez. We're trying to build up this giant sphere out of all these different sized bowls. And so this can't be big R. It can't be the radius of the entire thing because it could be any one of these shells. And you could also use just little r, but I know from experience, I don't want to do that because the next 2-3 problems, you'll see why. So the idea is each one of these has a surface area 4 pi r squared. Each one has a thickness dr, that's the thickness right here. And so we're going to integrate that out. And oh my gosh, what are we going to get? It's rho. There's a 4 pi. Now when I integrate r twiddle, that's going to give me r twiddle cubed over 3. And then I better put some limits on this. Think, what's the smallest size bowl that we're going to have inside this solid sphere? In this solid sphere up here, sorry, there we go. In this solid sphere, the smallest bowl you could have would actually have 0 radius, right? If you had a hollow sphere, it started something else. But so this is going to go from 0. And then the largest size bowl, remember, we're not looking at the diameter, we want the radius. So it doesn't go to 2r, it's going to go to capital R. So that means we got to evaluate this crap at 0 and capital R. And oh my gosh, I'm going to get 4/3 pi r cubed. I got a 4/3 pi r cubed upside down, and you end up getting Q. It will work out. And just so we could screenshot through the math to get through it faster, that's right here. You could see all of this stuff. That's what I was trying to get at. This green circle in here in the solution, this green circle is supposed to be the bowls that are building up the sphere. And you could see, oh my gosh, we get the right answer and yay. Okay, so it seems very circular, but I just wanted to make sure you feel good about using the mechanics of this. All right, so give me just a second. All right. I want to pause and see, are there any questions here? Is that okay? Okay, Tom, we're looking at a cross section. So it's really hard to draw spheres. Again, if I could, you got to think we're not building up a disk. What we're doing is we're building up this entire volume. So, right, each one of these takes up space in 3 dimensions. It's not much in the radius direction, right? This radius direction right here is very small. Whoops, right there. But the idea is if you build this up, you would get a solid, if you put enough of these together, here's another way to think about it, Tom. Imagine you have an onion. If you have an onion and you cut it up, haven't you built a solid sphere out of a bunch of slices that kind of look like these bowls? And maybe that helps you imagine it. Is that better, Tom? Yeah. So think about an onion and imagine if you were trying to build up a cylinder, right? I'm glad that lid was on. I would have poured it all over my crotch. If you had a cylinder, you could build this thing up out of PVC pipes, or you could think about a paper towel roll and build things up that way. Yeah. All right. So your homework is to eat as many onions as you can raw by tomorrow. All right. Yeah. Or maybe not. I'm losing it. Okay. Let's get back to work here. There we go. Okay, so we did this. The reason I did this one, yeah, if only it was that easy, right? Okay, so all right. So now you might wonder, I want to go ahead and jump into the next problem on the next page. So the reason I did the uniform is so that you could see how the uniform and the non-uniform examples are almost the same. So I'm looking at this next page. The idea is, and I'll bring this up in just a second here. Oh, did you have a twiddle question? I didn't hear it, Ryan. Did I miss it?
Yeah, is that the technical term for whatever you're doing there?
Oh,
Is
no.
that real? Oh, okay.
Yeah, R tilde.
Okay.
Right. So that the enye symbol looking, well, it's not an enye, right? The enye is the N with the tilde on it. So that little curved symbol is R tilde. But yeah, I just call it R twiddle for fun for some reason. Yeah, I don't know why. It just kind of stuck for me. Yep.
In calculus, we would use like sub I typically
Yeah.
for something similar. Like,
Yeah, for sure. That would work as well. Because you think about this, this is essentially a sum. This is like the sum symbol here. This is like the Riemann sum right here. Oh, geez, come on, annotate. This means sum of the ith radius, and then you could do it that way and think of it this way. It's totally the same thing. So the point being, you can't just call it capital R, and I don't want to call it little r or R sub I. This is what I chose to call it, and it doesn't really matter. You could call it R sub I if you want. That's totally fine. Good questions. Others? Okay, cool. So now this whole problem right here is just to show you what happens if you have a non-uniform. I'll get to that question in just a sec. What if you had some non-uniform density? And this is where you have to be a little bit careful. Look at the subtle change that I did. See that enye on there? Geez, I keep calling it that tilde on there, that twiddle. Okay, the idea is this. What if we have these bowls and each one of these is made from a different type of plastic, right? So maybe this was made from depleted uranium and it's extremely dense. It just looks like plastic. How do you know? It's a Zoom class. All right. And this one maybe is made of wood and this one's maybe made of cheese. So whatever. The idea is each different bowl could have a slightly different density. And the idea here is if each bowl has a different density, in this case, this is saying as you go to a larger and larger distance from the center, as you go to a larger and larger radius, the density of these bowls increases. So let's say this is made out of styrofoam, then metal, and then depleted uranium. And so they get more and more dense as you go out, except we're not talking about mass density. We're talking about charge density. So this could be an electron cloud that has very little charge at the center, and it becomes more and more charged as you get to the outside. Okay, something like that. And now there's a lot of chat. Let me check. Okay, cool. So let me see here. Yes, correct. All right. And Nate Dogg, is that a cool video you found? Go ahead and speak up. What's the story there?
You said onion, and it's about onions.
Oh, okay, gotcha.
It was just a funny commentary video.
Oh, right on. My bad. I didn't know if that was something I need to know. All right, you guys are on it. Okay, cool. All right. And then at this point, the idea here is in the real world, we may encounter situations where we have non-uniform charge density, maybe in a semiconductor substrate where the charge is deposited more heavily on the surface than down low, whatever. So it's possible you might have this kind of situation. Or just like I said, an electron cloud, the density of the electron cloud might vary with radius. And it absolutely does. And so you could see this is a way that you could actually figure out the total charge if you know the density. And that's the point of this. If you know the density, you can figure out the total charge. That was the point of this problem. This is the work, and you can kind of go through that. You could see, notice I checked the units right here. So here I get the units of this problem and check it out and make sure it, and then if you're curious, what happens if you have shells? Notice if it's uniform, well, if it's it's basically the same thing, except your inner radius is no longer 0. It might be from radius A to radius B, and all the work is exactly the same. If it's uniform, watch out. This is how that example works out. So I'm going to pause again for a second. So you could go through those examples later when we're not in such a rush, but that's just a brief introduction to how you can deal with charge density that has a volume component for spheres. All right. And I believe we're going to start working on this. Yeah. All right. So this might be the logical spot to take our 5-minute break, and then we can come back at 5:55. Oh, 5:56 now. All right. But are there any questions before I send you off to the break here and use the restroom? Doing all right? Okay, let's take that quick break, and then we'll come back and we'll see if we can go through a real Gauss's law problem in just a minute, all right? So I'm going to use the restroom and get some more water. What do you think, Jenny? Is that like PTSD for you?
Yeah, actually, I was just thinking that earlier. I was like, wow, this is bringing back a lot of memories, both good
Yeah.
and bad.
Isn't that crazy? Did you see the solutions in the workbook have gotten a little bit better, huh?
But yeah, it looks a lot cleaner. I like the colors in there. There wasn't colors before.
Exactly. Yeah, it's a work in progress, but it's pretty close now. There's still typos, but it's getting a lot better. Yeah.
Oh yeah, I can tell it's looking way better than it used to.
Yeah, for sure. For sure.
So
Took
it still
lots of
looks pretty
sacrifice
rough.
on your part. Oh, sorry. What'd you say? I was talking.
Oh, it still looks rough though. I gotta say, I think it's not so bad right now looking at it because I just recently had to do a lot of that kind of math in
Uh-huh.
one of my other classes, but still a little traumatic to see your workbook all over again.
Yeah, it's torture. Torture for sure. I'm gonna catch up on the chat here and see what they've got here.
Oh,
Okay.
just talking about internships.
Oh, I got you. Okay.
They said they might not require
Right on.
those
Was pipelines was that one that was like a really short one, like a 2-week?
No, that one was an 8-week.
What was that really short one they used to have that was like easy for community college students to get in and just have something on
Yeah.
their resume? Was
trying to
that
remember what
inset
it was
or
called. Inset is one of them. Yeah, there's a couple of them. Inset was one of them. I don't remember what the ones are. Oh, the one I did was called Cook Bridges. I don't think they do it anymore.
yeah, they
There's
probably have
still
a
lot of
different grant
schools.
now. Yeah.
Yeah, it's a different grant now, but all of those programs are still there, and those are great because they're specifically for transfer students and community college students, so they really
Right.
help you get through, transitioning to university as well.
For sure. For sure. Yeah. And of course, right, you stand out. It's easier to get in if they're looking for community college students specifically, right? Because it
Yeah,
filters it
absolutely.
into this crew of people.
Yep.
Yeah.
Yep.
Right on. All right. Oh gosh, I guess we should go and do a real problem here. I can't believe Jenny's brave enough to sit through this, and yeah, I'll be interested to talk to you afterwards too if there's time. But
Sure.
let me keep grinding away here. All right. So I think we talked a little bit about this. Okay. So page 36, I think this sums it up. If you don't care, move on. If you want to know when a thin shell is considered a thin shell, I did this for you. So if you want to know about that, great. That's there for you to read. We're moving on. Okay, so I didn't see it. Okay, so they said they might. Okay, I'll let Jenny answer that if she wants there in the chat. Okay, so if you care about when is a thin shell thin, just kind of read this and I walk through it and you can read it all. Okay. Okay, so now great. Let's move on. Now we're gonna do. I have a few more comments here. Oh, whoops! This page number is out of date. Let me find you the new summary page. Okay. Oh, there it is. So the practical summary is now on page 40. So I'm going to write that down. This is page 40. So if you're following along, the note at the top of page 37, right here, this should say page 40. Sorry about that. My bad. I moved it around a little bit. Okay. So now, let's take a look at this problem, and it's maybe going to see a little bit crazy, but let's start here and then I'll go to the whiteboard. Okay. So suppose we have a solid insulating sphere. So insulating meaning not a piece of metal, it's a piece of plastic, and positive charge Q, capital Q, is distributed uniformly throughout its volume. So this is very similar to the first density problem we did. Assume we are interested in points outside the sphere. And then just so you know, I'm going to use red for Gaussian and blue for, okay, got it. So what I want to do here, okay, is I want to look at the electric field. And what did I do? I said use red for the Gaussian surface. So this, you could imagine this one right here. Let me actually do it this way. This surface here, you could imagine is the red surface. I want you to think of this as the Gaussian surface. Okay. So now in this case, the what did I use? Red is okay. So I've got dA. Again, this is a sphere. Whoops. So I've got a little arrow here. That's a dA. I've got a little arrow here. That's a dA. These are all dA vectors, okay? And they're all supposed to be the same size. I'm a little sloppy here. But the idea is the dA vectors are supposed to be pointing radially outwards. That's the definition of those dA vectors, even one up here. So those are all my dA vectors, okay? They're small amounts of area at the surface. And again, this is not a plate. It's a sphere. You got to imagine we're looking at an onion and we're looking at an imaginary surface, like an onion inside a balloon. So imagine this gray object is the onion and this dotted line is a balloon surrounding it, okay? Whoops. Oh, geez, I just erased them. All right, whatever. We'll just draw two. There's two dA vectors. Now, the electric field is also pointing outwards. Let's use a different color for that. How about some blue ones? The electric field right here is also pointing outwards, right? It's away from the charge. And imagine if this is uniformly throughout, I suspect you could believe that by symmetry, the electric field should always point straight away from this center, okay? Now notice little r here. Notice I use this symbol little r. Little r is going to represent this red surface's radius. And this is why I now have three different radiuses, three different radii or whatever. I've got this one, which is the radius of the sphere. This one, which is a radius of the balloon that is outside this sphere or outside the onion. And then if we need it, remember, we could build this thing up out of little ones that I've been calling r twiddle. Now, we may not need that, but those are the three radii that we're going to be dealing with. We've got the radius of my Gaussian surface, an imaginary spherical surface. If it helps you think about what the Gaussian surface is, that's this. The Gaussian surface is like this clear white surface that I'm talking about there, right? It's this imaginary surface around the point charge. The point charge has some radius too, all right? So there we go. Let me get back to that. Where is it? Okay, so right in here. Now, hopefully you noticed at all points, the electric field and dA were parallel to each other. All right, so now I'm going to the whiteboard. Whoops, speaker view, there we go. All right. So here we go. Now, I'm going to tell you straight up. This is a part you could probably listen to and not write down. So if you just want to listen right now, that's fine. You've got the workbook if you actually need it later. I would just listen and not actually write anything. We're going to use the result of this over and over again, but we never have to do the work again. Okay, so, whoops. Where'd it go? Here we go. So we have some charge here. We know there's these electric field vectors pointing out at different spots. Now we know there's this imaginary surface. This is again in our onion of charge. We've got our imaginary surface that's supposed to be spherical. Sorry if it's not. We know that there's an area vector right here, dA. Same at all of these points. And because of the symmetry of the situation, because we used a spherical surface around a spherical charge, we know these are always going to line up so that they're always pointing the same way. I hope you believe that these two are always going to be parallel no matter where you put them. And that's what I wanted to point out. In that case, look at this special thing. The integral of E dot dA can be simplified. Because they're always parallel, you could think of this as being E times dA without the arrows, and then it's in the r hat dot r hat, right? The electric field is always radially outwards here, and so is the area vector. So this goes to 1. And this is really cool because it means now we don't have to do vector calculus. We can do regular calculus. And this is the part that you can skip every time. You'll be like, oh, if you're wondering why to do this, this is why. And now you know. If you don't want to remember that and just want to get this class over with, that's fine. Now, so this disappears because that's just the number one. So now we've taken this harder looking integral to this slightly easier looking integral. But wait, there's more. Ladies and gentlemen, what can you say about the electric field magnitude at all these points equidistant from the sphere? Somebody unmute and tell me. I appreciate it.
It's the same.
It's the same. So what does that say about this? What can we do with it? Trey, I guess you were crazy enough to speak up. I'll let you tell me.
It's constant, so you can pull it out.
It pops right out. Sweet. Thanks, Trey. Appreciate it. And so now, wait a minute. Now I don't even have to know what dA is. That's just going to be, a Canadian says, somebody other than Trey. What's the integral of dA?
Hey.
Hey, sure thing, eh? Don't you know? Oh, I gotta say a little Gauss's law, don't you know? My Canadian accent's pretty bad. All right. So this is really cool. And this is what I wanted to point out. If we're doing Gauss's law problems, we could go from a sphere with a spherical surface and just say, hey, I don't need to do this integral. I'm going to go right to here. And that's what we're always going to do so that we don't have to do this step of calculus. Yes. All right. I like calculus too, but don't get me wrong. Okay. So that's what allows us to take this crazy looking vector integral and just say, it's just EA Sports here. All right. All right. Got it. So that's what says this is equal to E times A. Now think, somebody else, somebody new. What's the area of this red sphere? Remember, this is imagine this is an onion and this is a big balloon all the way around it. What's the area I should use? Somebody unmute, will you?
4/3 pi r cubed.
Careful. That's a volume, right?
Oh, right.
So what will it be?
Surface area.
Yep. And that's what I was looking for. If I don't ask somebody, then it doesn't stick. So now it'll stick for you, right? Because we're so used to doing volumes from the previous problem. We're like, oh. So what should it be? Does anybody know? Here's a trick. If you take the derivative of the volume, you get the surface area. Take the derivative. Right? So if you can't remember that, that's how you do it. You know the volume, take the derivative, you get the surface area. That's not always true for all shapes. Okay, it's true for a sphere. All right, okay, so now, wait a minute. What radius should I use? Ryan, I guess you were crazy enough or nice enough to speak up, so I'm going to pick on you. Do you remember what radius do I use for the red area?
I don't remember which one you called which, but I think it was little r.
Absolutely correct. So this was little r. And so this would be 4 pi little r squared. All right. This is usually the part where people who had to retake this class start to puke because they know what's coming. You don't. it's you really have to pay attention to whether I use a capital or a lowercase letter or a twiddle. There's no it just sucks. Okay. You got to really be sharp here, people. All right. So now we have figured this out, but wait a minute. What does this mean? Remember, we defined this earlier, this funky ass integral. This had a name in physics. It was something, maybe you can guess before I finish writing it. Rhymes with trucks.
Electric flux.
Very good. You win a prize. Okay, so here we go. We've got electric flux. Wait a minute. Isn't this a closed surface? Imagine this is a point charge in here or something, and this balloon's all the way around it, right? Isn't there something else we know here? What was the electric flux equal to always when you have a closed surface, Mr. Gauss?
Equal to the charge.
Yeah, careful, not the charge, but the charge enclosed over epsilon naught. But yeah, basically the charge and a constant. Nice job. Was that Alexis or something? Yeah. Oh yeah, Jay, you got it too. Very good. So this is how we're really going to use this. I know this seems really circular, but check this out. How do you use Gauss's law? You take an object that has some charge on it and has some charge density of some kind. Then what we do is we write down this for a surface that happens to perfectly match the object. Then if I know how much charge is inside, I get the electric field right away. That's super cool. So what we're going to do now is we're going to play this backwards and say, I know that if I choose a surface that matches the object, I can write down this. I can find the area using some book that I read about cylinders or spheres in geometry as a kid. Then what I'll do is I'll say, well, I know by definition, this must equal Q enclosed epsilon naught. If I could use my integral calculus to figure out how much charge is here using all that density crap, or just know how much charge is in there, I can then figure out the electric field. That's a new way to figure out the electric field that in certain special cases of perfect symmetry is really easy, kind of ish. All right. Now, let's take a look and see what I forgot. And I'll see the chat question here. Okay. There we go. All right. So there we go. Come on, computer. Come on, any day now. I don't know. This was my favorite part of undergrad physics, right? It's like, I don't know why. I just love this. So if you could tell I'm getting a little bit excited, I'm sorry we're not in class together to have more fun with it. But wait, what problem are we on now? Geez, 23.5. All right, so here we are. Here's that problem in a different way. You could kind of follow it through. This is all the crap I was just saying, but this was the big deal. This is a lot easier equation to work with than this big ugly one up here, right? So if we have all of these things being true, we can use this, and this tells you why. So now look at this. I'm just going to skip down here to the result. This is the electric field for little r, my Gaussian surface, larger than the radius of my sphere. And I get this junk here. Q in is the amount of charge enclosed. In this case, somebody knew how much charge is the red surface enclosing in this picture. Some of it or all of it? Remember, it's like a red
All of
balloon.
it?
Yeah, all of it. So that's why I used capital Q. And I appreciate the feedback. It helps me out just so that I'm not just talking to the screen. And so that's how I get this. And remember, K is 1 over 4 pi epsilon naught. So, oh my gosh, you may be saying, wait a minute, isn't this the second day of class? And you're absolutely right. We just rederived the second day of class. That's a lot of work to rederive something we've been using for weeks. Oh, thank you, both of you. Okay, but now this is where it gets special. Now we can actually look at the electric field inside the charge object, whereas before we couldn't. We were always restricted to outside of a point charge. What am I saying? Now look at this. What if we go inside the object? All right, I'm going to start drawing up this one on the whiteboard. And now this is something we couldn't do before. 23.5, big deal. It's just like a point charge. Who cares? But let's look at 23.6 and see what is the electric field inside. Inside. All right, so I'm going to draw it while you get it set up. Okay, so now we're somewhere inside. Okay, so we've got this thing. Remember, in this problem, that is capital R. Okay, that's the radius of the solid sphere. This is some sphere that has some charge. It's a piece of plastic that's been charged up somehow. Okay, all right. So now, this is called the Gaussian surface. This is my imaginary surface. And so this has that radius little r. It's not really there. The red dotted lines do not exist in the real world. The blue lines do, right? That's the real object. And what this is doing, it's just kind of like a marker to say, well, how much charge is going to be enclosed inside of here? That will help me figure out the electric field at this point. So again, if I enclose this much charge, that helps me learn about the electric field at this point. Now, we're going to try and build this up. And remember, Kyle was here the other day and I threw my green marker, so I forgot to get another one. So I'm going to have to use a different color. Sorry. So in the solutions, this is in green. Sorry, I don't have all the colors. So imagine we're going to try and build this again. I'm trying to draw one of those bowls. So this is one of the onion layers building this thing up. Or again, trying to build up this whole thing out of these bowls, all right? And we're looking at, this is the cross section of this bowl, and eventually we're going to build up all of these. So now we're only going to go out here to this size, right? To this. So we're not going to use every single bowl. Maybe we only use these two and figure out how much charge are on these two bowls, because these two bowls actually fit inside the red surface. This one doesn't quite fit, maybe, and so we won't worry about the charge on this one. So now we need to be very careful. If we want the electric field here, we have to add up all the different bowls or all the different layers of the onion that actually fit inside this imaginary red surface. This is a very abstract concept. So if you're thinking, geez, this is weird, you're right. All right. So, and this radius here to this spot, that's going to be R twiddle. That's the radius of my bowl. And like we were doing in calculus, you guys said, oh, we'd like to call this R subscript I. So if you want to do it that way, you could. So just to get a little closer here, that's supposed to be an R twiddle. You've got the workbook if you need it. And then notice this, the thickness of this, the thickness of the bowl is dr twiddle. So again, we're going to build up and try and figure out how much stuff is inside of this portion of the blue bowl. So we only want to figure out this amount of charge because that's the amount of charge enclosed, and that's what matters for Gauss's law. If you're wondering why this doesn't affect it, we'll talk about it when we're doing coding. Okay. Oh, and let's see. Can we say that the Gaussian surface will always be the same shape as the object? Yes, kind of. For spheres and cylinders, we will. And then I'll talk about the exception of flat surfaces later. But yes, we're not going to do Gauss's law unless it matches, because then it's really hard and you have to use a computer anyways. Okay. So now when I look at this one, check this out. The electric field for little r less than big R. So I'm looking at the electric field in here times the area. And again, where is this coming from? This is the electric flux, which, if you remember, was the integral of E dot dA, which becomes this. All right. So the integral of this, the electric flux, whatever, that's EA. By Gauss's, I mean, Gauss was a genius to figure this out. This is crazy. What he's basically saying is all the charge outside doesn't matter. It doesn't affect the electric field. Shouldn't this one affect this point a lot more than all these others? Turns out, no. It's insane. All right. Anyways, whatever. I think it's crazy. EA is Q enclosed over epsilon naught. This is why Gauss is considered basically one of the one or two genius mathematicians of all time. One of the reasons. But yeah, so the idea is I only need to figure out this charge enclosed. And just to emphasize that, let's maybe draw that in red. I need the charge that's inside the red surface. Okay. In this case, this is where all the work comes. Now, we only have part of the charge enclosed. How do I get it? Well, that's easy. You know how now. Q enclosed is always going to equal the integral of rho dV. Now, here's the part that gets tricky. What is dV? What is rho? In this case, I think it would help. I'm going to run out of room. I would say it like this. This is the volume of one shell. So think to yourself, I want to build this stuff out of these shells. I need the volume of a shell. So I need a twiddle. right? So I need the volume of the purple shells. Again, I take the charge on this bowl, the charge density of this bowl times the volume of this bowl. That's 4 pi r squared times thickness. And that will give me the charge on this one bowl. And then I do that again with the next bowl and just keep adding up the bowls and make these things and make the shape. So now, yeah, and in this case, I think this problem is uniform, right? I think it was uniform. Yeah, it says uniform. So uniform is Q over 4/3 pi r cubed. And this is where we have to be careful. We need capital R because that's the total volume and the total charge. Q total over volume total is rho. So that's my density that I could plug into right here. You can see I'm having trouble with the whiteboard here. I'm running out of space. I really need to go to the solutions now. Sorry, I can't keep going on the whiteboard. Normally this would be like a whole whiteboard's worth across the room, but yeah. I see there's some chat there. Okay. Man, I'm so not cool. I don't even know what that means, Nate Dogg. What does that mean? Or is that just the sound of the bowls crashing? Oh, right on. Gotcha. Okay. Okay, that's great. Big deal. Here we are. So again, apologies for the red-green colorblind, but so we're trying. I'll try and also draw it here as I go. So here's the surface. That's the bowl that we're trying to build this thing up out of. You got your Gaussian surface, and so okay, let me get down here. I think we already talked about that on the whiteboard anyway. So. Okay, so this is, again, what you can always do. So this is what we just talked about a minute ago. We already knew this is what the volume is. So there's all the words if you want it. The smallest radius is 0. This is where it's a little bit special. Look at that upper limit. Little r. Notice we're not going all the way out to the edge to big R. We do not want all of the charge. We're only enclosing this amount, little r. That's why for this case, you're integrating to little r, whereas in the previous problem where we were talking about the entire charge density, or sorry, the charge on the entire sphere, we went to big R. So we get all this stuff. Okay, great. Always check the 0 limit in this class. Always check it. Now we're going to keep cruising along, blah, 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 blah. And this is, you could just follow this work along. And I know I'm racing along. I'm just looking at the clock, all right? The fact remains is you could do a bunch of algebra. You could follow it along. Here's that density. I just shoved it in. I found all this stuff. This is the cool result. Okay. Now I'll let you pick this up next time. I know you could always watch the live stream and go through the steps or whatever, but this is what I'm trying to do. Organize these results. We found this was the electric field when you're outside the sphere. And this is the electric field when you're inside the sphere. Now we have learned something new that we didn't get before because of Gauss's law. We're going to do our same old checks. Do the units make sense? K is on top. I got coulombs on top, meters squared on bottom. Look at this. There's a meter, meters cubed. That's meters squared on bottom. Both of these have KQ over meters squared. So that's good. Now this is another new check. I'll be right with you, Rye. Okay, so then this is the new check. Do the equations match at the boundary? In this case, what do I mean by that? Capital R was the one special radius in this problem. Think about that. At this one special radius right here, this is where we see the two electric fields should match up. The answer for outside, right out here, should match up to the answer for inside, right at the boundary. And so what you can do is take these two formulas right here and plug in capital R. If you plug in, whoops, right here, I'm trying to read this line. If you plug in capital R, the two results should match. And then there's a plot, and I'll let you absorb this while I answer Ryan's question here. Ryan, go ahead.
Okay, you kind of started talking about it. My question was more along the lines of the capital R. And so you were saying that the charge doesn't matter. The amount of charge outside our Gaussian
Surface.
Ball or whatever surface, yeah, didn't matter as much. But where it does matter is
it doesn't matter at all.
at all, but
if
it's in our
you have perfect symmetry.
Right. Okay. But it's in our equation or our definition for rho.
And so it does matter in the sense of that's how it factors in. You're absolutely right. He's saying capital R does show up in the answer because it's in the density. It's hidden in there.
Okay. Because we're looking at that entire area instead of
volume,
the other
entire volume. Yeah.
Entire volume. Yeah.
And so remember, this is another thing about this. We're going to have, so you can imagine why students hate this section. You have areas on the left from the flux integral. You have volumes on the right from the charge density integral. And so, and then we've got 3 different R's. And so to communicate with people, you've got to find a way to speak clearly. So I tried to do my best to color code them in here. But again, you know, if you're colorblind, that doesn't work for you. So I also tried to use different symbols. So the little r means always the radius of the Gaussian surface. Capital R should mean always the radius of my object. And then the R twiddle is the kind of the dummy integration variable that I use for the bowls that I'm building up the object. Sorry, Ryan, did I address your question or did I start rambling? Or
yeah,
both?
no, that was good. Yeah.
Okay. All right. Now here's something right here. If you're going to plot this thing, here's something that you should learn how to do, and this may help you. Oh, there's another chat question. Yeah, and you could, yeah, so if you're into triple integrals, you can totally do that, and then you don't have to know these tricks. But so again, since that's the not the prereq for this course, what Alexis is saying is right here, if you have already had triple integrals, this DV is actually really easy for you because you already know about the Wronskian and the Jacobian and all these tricks and all that. But we don't know that in this class, so I can't do it. But you're absolutely right. If you could do 3D calculus, go for it. Okay, so I'll be honest with you. Normally, when I do this class paper and pencil, I'm super hardcore about the plots. All right? Now, I'm trying to think. There might be something about the plots on the final exam. So I'll probably put at least one plotting question. But now you might have just lucked out because of COVID. If you have to ignore something for this semester, it would probably be the plots for the Gauss's law, because I put a lot of work into that, and I think you can learn a lot from it. But I'm not sure how I'm going to be able to test you on that. I know I do a lot with plots later in the LRC circuits, but that's totally different. I'm just, you should still maybe do it at the beginning. And here's a trick. I'm going to show you a trick really quick. Since you guys are working at home, you could use this during your quizzes, and that won't bother me. You can actually use Excel during your quiz if you want. You can't use other people's Excel sheets or other people, but right, one of the things you can do here, let me just make this a little bigger so it's easy to see, right? We have these 2 formulas. One of them said something like E equals KQR over R cubed. And that was one side. Oh, oops. And I'll get to the question in just a second. And this was inside, right? That was the formula inside, and then outside, and apologies for the formatting, but let's just get this damn dumb thing done. So this was KQ over little r squared. And this is where you have to be careful, people. The little r's and big R's do matter in the final answer. Think about it. Capital R is a constant. Okay, this thing is a constant, right? And these 2 things here are also constants, right? The K, the Q, and the R are not changing. And what we see here is this little r is changing. That thing is changing with time. Now, over in this answer, both of the things in the numerator are constants, but this one is changing. And let me get to the chat question really quick. Alexis, I think what you will find is they're not wasted because you're going to understand it a lot better. So, and I'll probably put it on the final, like I said. So, but yeah. All right. Now here's a trick. What you can do is if you want to plot this thing, you can make a table. And then what we're going to do is cheat and say everything has units of 1. So this would be just R. Let me do it like this. R is 0, and let's just say 0.1, and then I'll fill this down. Let's just go out to like say radius 2. Let's make this just so this takes up less room on the screen. All right. All right. So the idea is that's my radius. Sorry, this I can't help it. I got a format. All right. So now this would be the radius in units of big R. And what do I mean by that? This, come on. There we go. Right here, this is supposed to be the little radius as a fraction of capital R. So right here is the special case. These ones are all inside. So right here, let me shade these ones. These all would be inside the sphere. All right. And so here I could put the electric field. And what I'm going to do is just take every one of these blue numbers and set it to 1. Right. So inside, the only thing that matters is R. Right. Now, and I'm going to need another number here. So what I'm doing now is there's usually a discontinuity right at the edge. And then I'll put in one more here. And then let's get rid of these yellows. And apologies if I'm wasting your time. I'm just trying to show you how I make these plots, all right? So the idea here is outside, it should equal this number divided by, 1 divided by this number squared. Where did I get that from? This formula right here. This is a 1. This is a 1. So I'm just taking all the constants and setting it to 1. Why? So I can get the shape. So now if I fill this down, I could rock that out. And then all you have to do is go in here like this, and you can get a quick plot. Oh, geez, I can't see anything on my Zoom. Oh, insert, scatter plot. There we go. And that's how you make these plots. So again, all you do is you set all the constants to 1, and we could label this thing. But if you're wondering how to make these, this is why I'm always like, why don't people just make these plots? They're so easy. Well, they're not easy for you because you haven't made them. But if you get in the habit of making them, when you actually need to make plots on the job, it'll be fast. If you don't, you're just going to be slow, and then people will be, maybe I won't hire them. Okay, so that's what that plot's all about. I know you've got the YouTube video, so I could cheat and let you watch it again later. Oh my gosh, I think that's. Did we do everything there? Oh yeah, there's some more stuff. We'll actually work this out later. Yay, we made it through the problem. All right, so let me pause for a second. Whoops, escape. Oh my gosh, that was intense today. All right, so let me get to the chat. Yeah, exactly, right? So it's always going to be good. You got to use plots all the time because nobody wants to see one data point in an Excel table. No one wants to see your Excel table calculating all the different points. They only want to see plots only. So thanks, Jenny. I appreciate the backup. Now I owe you like $100. Damn, I shouldn't have had you come to class today. All right. I know it's almost time to go. We got a minute to go. I do want to foreshadow this. What I did, if you want to read the book and get an edge for the next class, I'll just show you the next topic and then I'm going to call it a day. So if you look here in the book, the next thing is cylinders. On the next page, we're going to do cylinders. And if you care or if you don't care, here you go. So if you want to know thick versus thin, what matters, there it all is. And so now you're going to do this thing with the cylinder. The cylinder, I will say this very carefully. Typically, let me find this really quick. I know you guys are tired and want to leave. On page 50. So just give me a second here. Page 50. Oops, right here. I think. I passed it there. So when can you use Gauss's law versus, and by the way, this is page 50. So if you're wondering when do you use Gauss's law and when do you use the old method, and here it is. Pretty much any spherical cases, you could use Gauss's law. The one exception would be charge is non-uniform and it depends on angle. Okay, that's usually in your junior, senior year. I'm not going to test you on that. For cylinders, it's a bit more complicated. Gauss's law only applies in this special set according to this thing. Basically, if you're somewhere in this light gray region right here, if you're anywhere near the middle of the cylinder, like far from the endpoints, it doesn't work down here or down here. Then you have to go back and use chapter 22 methods. But if you're somewhere in the sweet spot, Gauss's law works. And then what you do is, if you're somewhere near the middle, you could pretend the cylinder is infinitely long, even though it's not, and actually get correct answers to 1% or less. So while this isn't a perfect picture, the idea is, again, cylinders are not as simple as spheres. That said, let me go back to where we were. I know it's time to go. Just give me a sec. Oh my gosh. I'm just trying to set you up so you could read at home if you want to, because this is pretty gnarly stuff. Okay. Oh, one more. You could try and follow this thing, and you'll notice that we're going to ignore the end caps down here. So these are the regions I call the end caps. If we ignore those regions and focus on this part, we could say the electric field coming out here is negligible. The electric field coming out here is negligible. And that's true whenever this is true. All right. And you could go through that, and here is the summary. So if you want the practical summary, here's what I would recommend. Try to do that problem by yourself. Try to do problem, oh, geez, I'm flipping pages now. Try to do 23.7 on your own. Now, I know you have a quiz to study for, so maybe after you do the quiz or whatever, I don't know. Maybe you won't have time to do this before the quiz. It'll be before lab. But that's where we're going to pick up next time, all right? So cylinders and these practical rules, and this is kind of the guts of that. All right, whoops. All right, let's go ahead and call that good. I'm going to stop.